Hello students. So we are learning matrix algebra. We have already done how to find eigenvalues and eigenvectors. Okay. So today we are going to learn the process called matrix diagonalization. Okay. So it is a process of converting a square matrix which is given into a diagonal matrix. Okay. So same steps you have to follow. That is, you have to find first you have to take the equation A minus lambda I, a determinant is equal to 0. So from that you will get the values of lambda, that is eigenvalues, and then you have to find the eigenvectors corresponding to those eigenvalues. Okay. So those eigenvectors will give you the matrix P, okay, which we will be using to find the diagonal matrix D. Okay, that you have to find P inverse also. Now diagonal matrix is given by the eigenvectors. The diagonal elements are the eigenvectors. Okay, and all other elements are 0 because it is a diagonal matrix. And one more thing, that uh, the values in P can vary. That is, diagonalization is not unique. Okay, so depending upon the values of x, y, z, okay, P can be any matrix. Okay. So whatever matrix you get, you go with it. Okay. So let's start with an example. So we have taken a 3 by 3 matrix. Okay, we have done a 2 by 2 matrix for eigenvalues and eigenvectors. So I'll take a 3 by 3 matrix now. Okay, so first you find out determinant of A minus lambda I equal to 0. Okay, you have to take this and solve the equation. So I'll directly write this. So it will be 1 minus lambda, right? 2 minus lambda and 3 minus lambda is equal to 0. Okay. So here I'll take this row. So going along that R1, we'll get 1 minus lambda into 2 minus lambda into 3 minus lambda minus 2. Okay. This is 0. Last one is minus 1. We'll get 2 into minus 2 into 2 minus lambda equal to 0. This will be 2 3 is 6 minus 5 lambda plus lambda square minus 2. Okay. So this is lambda square minus 5 lambda 4. This is minus 2. So this is minus 2 lambda plus 2 equal to 0. Okay. Take this inside, so you'll get or you can take, so multiplying this inside you will get lambda square minus 5 lambda plus 4 minus lambda cube plus 5 lambda square minus 4 lambda plus 2 equal to 0. So minus lambda cube, lambda square and 5 lambda, this is 6 lambda square minus 4 lambda minus 2 lambda minus 6 minus 5 minus 11 lambda. 4 plus 2 is 6. 0. Okay. Now you have to use synthetic division. Okay. So using synthetic division, you can change the sign. Plus 11 lambda minus 6 equal to 0. So the coefficients you have to write, right? 1 minus 6, 11 minus 6. So this we are doing to reduce it to the quadratic form. Okay, so that we can easily find the factors. Okay. So I'm going to take 1. Okay, this 1 comes here. Then 1 into 1, 1. Minus 6 plus 1 is minus 5. 1 into minus 5, minus 5. 11 minus 5 is 6. 1 into 6 is 6. This is 0. So till you get 0 here, you have to continue this. Okay. If it doesn't work with 1, then you have to go for minus 1, then 2, then minus 2. Okay. So whatever the factor you will get, this is 0. So 1 is the factor of this. Okay. So we can write this as lambda minus 1, 2. This is lambda square minus 5 lambda plus 6. Okay. So this is our, so if you factorize this, you will get, this is product is 6 and the sum is minus 5. So you have to take 3 and 2. Okay. So this is minus 3 minus 2. 3 to the 6 and 3 plus 2 is 5. Okay. So the final is lambda minus 2. So you will get eigenvalues as 1, 2 and 3. Okay. These are the eigenvalues. Now corresponding to this eigenvalues, you have to find the eigenvectors. Okay. So finding eigenvectors, okay. So start with lambda is equal to 1. Okay. So if you put lambda is equal to 1 in our equation A minus lambda I, you will get it as, so A was 1. So 1 minus 1, 0, 2, 0, 2 minus 1, 1, 3 minus 1 is 2. Okay, you have to take the equation A minus lambda I into x equal to 0. Okay, to find the values of x. So I'm taking x as x, y, z, so that you will get the equations. So those equations you have to solve to get x, y, z. So I'll reduce this, okay, so that it will be easier to find x, y, z. So I'm reducing it. I'll take r3 minus r2. Okay. So 0, 0 minus 1, 1, 1, 1, you will get 1, 1, 1. So both the rows are same. So you'll get only two equations. One equation if you multiply, you will get minus x minus z is equal to 0. So your z is 0. Okay. Second equation is x plus y plus z equal to 0. Z value of z we got, that is 0. So x is equal to minus 1. Okay. So I am taking x equal to 1. So y is minus 1. Okay. So the eigenvector related to this is 1 minus 1, 0. Okay. Next is lambda is equal to 2. Okay. So we'll get 1 minus 2 minus 1. 2 minus 2, 0. 3 minus 2, 1. Okay. So if you want to reduce, you can reduce this. So I'll just take, here also two rows are same, correct? So I'll do R3 minus R2. So I'll get minus 1, 0, minus 1, 1, and this is 1, 2, 0. Okay. Again, taking the equations, let's see what you get. Minus x minus y equal to 0, that is same as x plus y equal to 0. Okay, and the second equation is this is 0, sorry, x plus y equal to 0. Okay, so from this you know that x is equal to minus z. Okay, so we can take this is 2y. Okay, so if I take you have to look for this values. Okay, this comes to x equal to minus 2y. So if I choose y equal to, say I'll take x equal to 2. Okay, x equal to 2, then y will be minus 1, correct? If x is equal to 2, then z is equal to minus 2. Why I took equal to 2? Because if I took 1, then this y value will be 1 by 2. Okay, so it will be like tedious work to calculate. Okay, so I can make it simpler by choosing the values such that the number is an integer, okay, or a natural number, integer, because minus numbers are also there. Okay, then so this eigenvector is 2 minus 1 minus 2. Okay, 3. So it can vary depending upon the values you choose. Lambda equal to 3. So A is 1 minus 3 minus 2 and 2, 2 minus 3 minus 1, 3 minus 3, 0. Okay. So here I can again reduce R3 minus 2R2 I can do. Okay. This will be 4 minus 2, 1, 2 minus 1, 2. Okay, so taking the equations, minus 2x minus z is equal to 0. Then x plus x minus y plus z is equal to 0. And 4y minus 2z is equal to 0. Okay, so from this you will get 4y is equal to 2z, so z is equal to 2y. Okay, so I'll put it here, 2y, so x plus y, x is equal to minus y. Okay, so I can put z equal to 2. Okay, so that I'll get y equal to 1. So put z equal to 2. So I'll get y equal to 1. If y is equal to 1, then x is equal to minus 1. Okay. So these are the values. So the eigenvector is 2, 1, minus 1. Okay. So the eigenvectors constitute your P matrix. So P matrix is 1 minus 1 0, 2 minus 1 minus 2 and 2 1 minus 1. Okay. And we have a D matrix which is made up of lambda 1, lambda 2, lambda 2. That is diagonal matrix. Okay. So it is 1, 2, 3, 0, 0, 0. So we have to show that E inverse AP is equal to D. Okay. So let's find out E inverse. So how to find inverse of a matrix? There is a formula, right? A inverse is equal to 1 upon determinant of A into adjoint of A. What is adjoint of A? Adjoint of A is transpose of a cofactor matrix of A. Okay. So please go through the video which I'll be linking in the description box. Okay. There I have shown that how to find A inverse, that is from 12th standard. Okay. So for a 2 by 2 matrix it is easy, that is adjoint of A for a 2 by 2 matrix if your A is A, B, C, D. Okay. For 2 by 2 matrix you have to interchange this, interchange, that is I'll write here, interchanging you'll get DA, and for this you have to change the sign. Okay. So this is minus B minus C. This is for 2 by 2 matrix. For 3 by 3, you have to go for a cofactor matrix. That is, you have to find minus and all. Okay. So I'll just write our cofactor matrix of P. Okay. First, you have to put the signs plus, minus, plus, plus, minus, plus, minus, plus. Okay. Now, you have to take this. You have to see the corresponding minor matrix. So take the determinant 1 minus of minus 2. So 1 plus 2, 3. Okay. Um, Inverse you have to find, right? Okay. Here I've written, I think Z is 2. Sorry for this. Z is 2, X is minus 1 and Y is 1. Okay. So your matrix, here also I'll check. X is 2, Y is minus 1, Z is minus 2. X is 1, Y is minus 1. Okay. Minus 1, 1, 2. So this is minus 1, 1 and 2. Okay. So cofactor matrix changes. So this is minus 2 plus 2. So it comes to 0. Okay. Then minus 2, 2. 2 to the 4. 4 minus 2. So 2. Then 1 into 2. Then minus 2. Then 2 minus 1. So 1. 1 minus 1, 0. Minus 1 plus 2. So plus 1. Okay. So adjoint of P is transpose of cofactor matrix. That is this. Okay. Transpose you have to write. So 0. This row becomes this column. 2, 2, minus 2, 2, plus 2, 1, 0, 1. Okay. So this is your adjoint of P. Now find out determinant of P. Okay, so 1 minus 2 plus 2, 0 minus 1, 2 to the 4, minus 2. So 4 minus 2, 2 minus 2. Wait a minute, what I did? This is plus 1. So plus 2. Okay, so this is the determinant of P. So P inverse is 1 upon 2 into 0, 2, 2, 2, 2, 2, 1, 0, 1. Okay, now we have to check for D. So I'm taking P inverse AP. Okay, so P inverse is this half 0, 2, 2, 2, 2, 1, 0, 1. A matrix is our 1, 4, 1, 0, minus 1, 1, 2, 1, 2, 2, 3. And P matrix is 1, 2, minus 1, minus 1, minus 1, 1, 0, minus 2, 2. So you have to multiply this first, that is A into P. Okay. So keeping P inverse as it is, I'm multiplying this, so we will get 1 into 1, 1, 0, 0, 1 into 2, 0, plus 2, 1 into minus 1, 0, minus 2, 1 into 1, 1, 2 into minus 2, 2, minus 2, minus 2, minus 1, plus 2, plus 2, 2 into 2, minus 2, 4, minus 2, minus 6, 2, minus 2, plus 2, and 6. Okay, so this gets cancelled, this gets cancelled, this also. One minus 1, 0, 4, minus 2, minus 4. Then minus 3, 3, and 6. Okay, you can write this number outside only and you can multiply. This is scalar which is multiplied to a matrix. Okay, so again multiplying you will get 0, 2, 0, 0, 2 to the 4, minus 4, 0, minus 6, plus 6, and 2 ones are 2, minus 2. I'll take here only 2 ones are 2, minus 2. Then this into this, 2 fours are 8, minus 4, 2 threes are 6, 2 threes are 6, 2 fours are 8, 2 twos are 4, 4 ones are 4, 2 threes are 6, 2 threes are 6, 6. Okay. So this gets cancelled. This is 0. This is also 0. Okay, so you'll get 2, 0, 0, 0 4 0 0 0 6. Okay, dividing we'll get 1 0 0 0 2 0 0 0 3, which is our diagonal matrix D. Okay, so we have diagonalized that matrix 8.